Chapter 6, Section 4, the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus has two parts, Part 1 and Part 2. The first part says if f is continuous on an open interval containing a, then for every x in the interval, this applies. So pretty much the Fundamental Theorem of Calculus, Part 1, is what pretty much confirms that the derivative, while at the same time integrating, will pretty much cancel each other out, or think of it as inverse. The derivative and integration are inverses of each other. So if we take the derivative with respect to x of an integral from a to x of f of t dt, then we just simply get f of x. Okay. Some other things that we learned from part 1 of the Fundamental Theorem of Calculus is that every continuous function f is the derivative of some other function, and we also learned that every continuous function has an antiderivative. Okay. Notice that, so pretty much all you got to focus on is this, but you do have to keep in mind that in part 1 of the Fundamental Theorem of Calculus, a is a constant, and we're going to focus more on just working out examples that deal with the Fundamental Theorem of Calculus. So if we look at an example where we are having to take the derivative with respect to x of the integral from 5 to x, notice that we have an a value that is a constant. So from 5 to x of t squared over t squared plus 1 dt, then believe it or not, applying the part 1 of the Fundamental Theorem of Calculus says that all we're going to do is substitute your top limit, x, into every variable in your function. So what we have is, instead of t's, I'm going to change those with x's. So we have that, or in other words, it's just x squared plus x squared plus 1. Okay, so we can do this if the top variable, the top limit is a variable that's just simply x, only x. Okay, the minute it becomes x squared or x cubed plus 2x or anything other than just simply x, then we have to find a different approach. But this only works when the upper limit is only x. So go ahead and copy that down. When the upper limit is x and the lower limit is a constant, this direct replacement method works fine. Okay, part 2 of the Fundamental Theorem of Calculus says if a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of lowercase f on the interval from a to b. In other words, what that pretty much says is that f prime, the derivative of capital F, so capital F prime of x, is equal to lowercase f of x. That's pretty much what that said. So if all of this applies, then the integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a. So the antiderivative of f of b minus the antiderivative of f of a. So this was important, or this is going to be very important, because this is actually the theorem that ties in the relationship between integration as the area underneath a curve, which is what you started this semester as, versus the integration as the antiderivative of a function, which is how we ended second semester back in December. So this is kind of what relates those two ideas, those two concepts. And let's look at some examples. Okay, so we have the integral from 1 to 3 of x cubed dx. Before I solve this, I'm going to go ahead and tell you that I'm going to go ahead and apply the theorem you guys just saw. So integrating from a to b f of x dx. Oops. That's pretty much capital F of b minus capital F of a. And I'm also going to include here, not just that, I'm also going to talk about what we learned at the end of first semester, which was integrating x to the n dx pretty much is the power rule, x to the n plus 1 over n plus 1. So I'm going to put these two into play. So what I'm going to do is I'm going to integrate x cubed using the power rule. But I'm going to keep, this is just a notation that I use. I use this bracket notation with the with the lower limit still in place and the upper limit still in place. So what we pretty much have here is x to the 4 over 4, keeping in mind that we have a lower limit of 1, an upper limit of 3, and then we go ahead and bringing this part 2 of the fundamental theorem of calculus. So now our function, our antiderivative is x to the 4 over 4. So I'm going to plug in the b and the a. In this case, the b is 3, the a is 1. So what this now becomes is 3 to the 4th power over 4 minus 1 to the 4th power over 4. And then we just compute to get our final answer. So we get 81 over 4 minus 1/4, or just 80 over 4. I know you can simplify that, but that's not what I'm trying to get across to you guys. I'm trying to get the idea across to you guys. So I'll just leave it as 80 over 4 as your final answer. Alright, here's another example. Integrate from pi over 4 to pi over 2 the function negative cosecant squared x with respect to x. So you will have to integrate trig functions on the AP test, so might as well start getting used to it now. So we don't use the power rule here. Quick refresher, quick reminder on that. We're not going to use the power rule here. We know that the derivative of cotangent x is negative cosecant squared x. So integrating negative cosecant squared x is just cotangent x. Keeping in mind that we have to put our limits from pi over 4 to pi over 2 after we integrated, and then we just plug in the values, or we just plug it. We apply the fundamental theorem of calculus that says capital F of B minus capital F of A. So we have cotangent of pi over 2 minus cotangent of pi over 4. So pause the video. You try to compute what cotangent of pi over 2 is. You try to compute what cotangent of pi over 4 is, and check it with mine. Cotangent of pi over 2 is 0, minus cotangent of pi over 4 is 1, so your answer should be -1. And for the last example, I want to go back to the fundamental theorem of calculus, FTC, part 1. So remember I said that whatever we're integrating, we're taking the derivative while at the same time integrating a function where the lower limit is not a constant. So notice that a is x squared. But more importantly, I also said that if the upper limit isn't simply x, we can't just directly substitute. We have to do more to it. Okay, this is what we have to do. I say this to the end because I'm going to use some concepts or some ideas of part 2. This is part 1. But I'm going to use some ideas or concepts of part 2 of the fundamental theorem of calculus. So what I'm going to do is I'm going to go ahead and that idea of f of b minus f of a, I'm going to apply that here. Okay, but I'm also going to think of the chain rule. So not only am I going to apply this, I'm also going to think of some ideas of the chain rule. So in short, this is what I'm trying to say, is this will be the integral. I'm going to plug in, for every t, I'm going to plug in the top limit. Start off with the top limit. Remember, it's f of b minus f of a. So the top limit, plug it in for every t. Okay, but on top of that, I'm also going to go ahead and take the derivative of that top limit. So x cubed plus x prime. And remember, it was f of b minus f of a, so minus, now I'm going to do the bottom limit. So it's x squared cubed plus 1. And then I'm going to multiply it times the derivative of x squared. Okay, and the final answer should, let's just keep it simple. It'll just be x cubed plus, whoops, that was supposed to be an x here. I messed up. So x cubed plus x cubed plus 1 times 3x squared plus 1 minus, we don't keep that like that, or just write x to the 6 plus 1 times 2x. That would be your final answer. If you have any questions, you can go ahead and ask me in class. That'll do it for this video.